webinar. Today we have in our midst Sebastian, who is going to educate us on deep learning for video classification. Before I hand over to our guest speaker, I would like to introduce him, read a little about him. Yes, so Sebastian is a final year student at Ashesi University and an aspiring researcher with keen interest in artificial intelligence and machine learning. He also works on projects involving using machine learning and multimedia data. Hello, Sebastian. Hello, Sebastian. Okay, thank you once again. You can please start with your presentation. Can you hear me?
So today I'm going to talk about...
Yeah, can you hear me?
Yeah, I can hear
Great.
you. Can you hear me?
Yes, I can.
Okay.
You can please go ahead.
Okay. So today I'm going to talk about deep learning for video classification. And first, let me say hello. My name is Gbetondji Dovonona, and Sebastian is easier. And I like working on projects that involve deep learning and multimedia data, especially when it comes to videos. So why would we like to use deep learning on videos? So the reason is that there are some problems that cannot be solved with images. I guess most of us are familiar with image classification because there's been a lot of talk on image classifications for solving various problems, but sometimes classifying images is not enough, and we need videos to be able to solve some problems. So some of those problems are problems like action recognition, sign language recognition, or automatic speech reading, which require video input. So let's talk about action recognition first. So when we talk about action recognition, we are looking at specific actions that are performed by human beings or maybe a machine or some other stuff like that. So let's say for football fans, one of those possible actions could be to make a pass or to shoot the ball, or it could be two people greeting each other or anything like that. So if we want to recognize an action, we need the full sequence, because we can't recognize, most of the time you can't recognize an action based on only one image. Sometimes it's possible. In the case of someone, let's say, holding someone's hand, you can say that it's a handshake based on only one image, but most of the time you can't do that. You can't just understand what is going on based on only one image. Another example is sign language recognition. Some signs can be recognized with only one image, like for instance one. I think that's it in sign language. With only one image you can see it, but for some other signs you will need a full sequence because they can't be shown in only one image. The last one is a project I worked on 2 years ago, which is automatic speech reading or automatic lip reading, which is basically being able to see or to understand what someone is saying based on their lips movements. So you have a video of the person's lips or the person talking, and based on that, you can determine what the person is saying. So that can be very useful, for instance, in order to generate subtitles where you have a video and you don't have the sound and you are not sure what was said. Typically, you would need an expert to look at the video and tell you what was said, but with automatic speech reading, you can just pass the video through a model that will give you the subtitles. So for this task, you would usually require a video input. So now, to understand how we can use deep learning on videos, we first need to understand how the video is represented by a computer. So our machines represent videos as series of frames. So the frames are normal images, so they're represented by a matrix. But now we have a series of them. So we already have models that can handle the different types of information that are in a video. So since it's a series of frames, the frames part means that we can use spatial information. So it's a series, right? Meaning that there's a specific order in which the frames come in. And that order gives you a form of information. And there are models that are usually used for a series or time series. So one of the most famous ones for that is the LSTM or aighana models. And you can also use convolutional neural networks for that. There are one-dimensional convolutional neural networks that can be used for a series. So now a few limitations of deep learning being applied to video classification or video data in general is an issue in terms of computation power. So deep learning is known to require a lot of data already, right? But then when it comes to video data, it requires even more data because a video is a series of images, right? So assuming you have a video that has 10 frames per second, for just 10 seconds, you already have 100 images, right? So if you have you need to look at videos that are 10 seconds and you have a data set with thousands of videos like this, that's already a lot of images, right? And processing all this can be quite costly in terms of computation power. So to give an example, when I was working on lip reading, automatic lip reading, the data set that we used was, okay, there are 3 data sets. The first one was around 70 gigabytes. The second one was around 50 gigabytes, and the last one was around 100 gigabytes. So the computation power that is needed to run a model on all this data at once is quite huge. So with our smallest model, typically it would take around 5 hours per epoch. And to get a good accuracy, you would need minimum around 30 epochs. So to run a model on all of the data, you are looking at several days of computation, and that's using the GPU. So the first limitation is the limitation of computation power. Now, the second one is in terms of complexity of the data, right? So here, what I mean by complexity is the number of dimensions. So typically, in machine learning, the more dimensions the input has, the more difficult it is to deal with that input. So, for instance, with data that is just like one-dimensional, typically it's easier to learn a model to represent that data. Images are harder to work with and require more data because they are two-dimensional. So it's hard to map them to a specific output. And with videos, because we add a third dimension, which is time, they become even more difficult to work with. Now, the last limitation that I faced was difficulty in handling the data. So for images, we have libraries that help us load images quite efficiently in Python. So there's OpenCV, there's, I mean, in general, yeah, there's quite a lot of libraries to do that, and it's typically very simple. But with images, with videos, it's more difficult, right? With CSV files, images, for instance, for CSV files, you have pandas. For images, you have OpenCV. For tabular data and machine learning on images are things that are done quite often. You also have a lot of code that you can easily find on GitHub or other platforms. But videos, you wouldn't find that easily code that shows you how to handle that type of data or how to just open it. Opening even an MP4 file usually requires at least 2 or 3 extra libraries that you need to load, and you need to learn how to use that. But apart from that, there are also other issues, like for instance, the differences in terms of dimensions between videos. That one is not really that big of an issue. And it's also one issue that is present with images. Sometimes you have images that are different dimensions, but you need to pass them through the same model. And since the model is kind of like a function, it expects a specific dimension for the input. So usually for images, you can use an input that is like 400 by 400, right? So with videos, you can have also different dimensions. And if you get an input that doesn't match the dimensions expected by the model, you can just resize the input. But one other problem that also needs to be looked at is the number of frames and the frame rate, so the number of frames per second. So if you have a first video that is, say, 10 frames per second and another video that is 5 frames per second, the frame rate is different. So you need to adjust the frame rates for all the videos so that they are the same. Because if you don't do that, then to the model, it will look like the videos are at different speeds, right? So if the model, for instance, expects a video that takes a video that is 10 frames per second, and you give it a video that is 5 frames per second, to the model, it will look like the video is 2 times faster than what it usually expects, right? And the issue with that is, even though for us human beings, we can usually deal with that kind of changes in terms of speed. So even if I show you a football match that is maybe at a 2 times speed, usually most people would still be able to tell that it's a football match. But given the already high complexity of video classification, for a model, even small changes like that can affect it and really affect the result and drop the accuracy when classifying. So yeah, those are 3 of the most common limitations of working with deep learning on video data. But there are a few solutions for most of them. So for instance, in terms of the complexity of the data, one solution is to use pre-trained models, right? So typically, you wouldn't find a lot of pre-trained models that are pre-trained to work with videos directly. But since most models that are used for videos are a combination of time series models and CNN models, then you can use pre-trained CNN models, right? So for most cases, you would use a model that is pre-trained on ImageNet. And that's great. That's really great for helping with the complexity of learning representations of videos. Another solution is to simply use lighter models. So Instead of using LSTMs, you can use CNNs, so convolutional neural networks, because they are much lighter, they're easier to make parallel, so usually they are faster than LSTMs. In terms of model size and number of parameters, LSTMs are quite big and heavy, so they are not always recommended. Apart from that, there are some convolutional neural networks that are meant to be smaller. Usually they are created to work on mobile phones, like smaller. We can use them in this case. So I once tried using a mobile net instead of a dense net and it worked great. But between these two, I found that using convolutional neural networks instead of LSTMs was way more efficient. So yeah, when I worked on the lip reading project, that's what the model looked like. That's the model that gave us the best results for the smallest model size. So you get a frame sequence which has this dimension, 1 by 29 by 128 by 128 by 1. So first let's look at these two dimensions here, the 128 by 128. So this is the dimension of a single frame. So here it means that the frame, so each individual image in the video has the dimension 128 by 128. Now you have 29 of them. So each video had a fixed size of 29 frames, right? So yeah, typically you would use videos of a fixed size, and if the video doesn't reach the maximum size, you can use different padding methods to pad for it. So if, let's say, you are expecting, the model is expecting 29 frames and your input video is 20 frames, you can repeat the last frame until it reaches the whole 29, or you can repeat the video itself, right? So that's the 29 here in that dimension. It stands for the number of frames. So you have 29 128 by 128 images. Oh yeah, there's the one here. For most videos, it will be a 3. So the 3 here stands for the number of channels, because with most images you have RGB channels, so you have 3 channels. But for our lip reading project, because we found that lips in black and white and lips in colors don't really make a difference, we decided to go for black and white, because that will make the input 3 times smaller and will make the model around 3 to 4 times faster, which is great. And here, this one is just the batch size. So the number of videos you are passing to the model at once. So one thing that helped was this. This is something that was quite recent at the time, which is what they called a spatial temporal front end. So here, spatial temporal, because it extracts features that are at the same time spatial and temporal. So the video has 3 dimensions, right? The height and the width of each frame, and also the time dimension. So you can use 3D convolutional neural networks to extract features from those 3 dimensions at once. So we used 2 layers of this to extract features from the 3 dimensions at once. And then we had a 10-layer time distributed dense net. So here, what the time distributed dense net means is that you have one single dense net model. But now that dense net model is going to look at each of the 29 frames separately. So that's the reason why it's called time distributed, because it's going to be distributed alongside the time axis. So the DenseNet here is going to take each one of the 128 by 128 frame. So there will be 29 of them. And each of the inputs, the 29 inputs from the DenseNet are going to be concatenated together, which will give you a series of length 29 that you will give to the ConvNet for learning features from the series of outputs from the DenseNet. So that's actually how the combination between the DenseNet for extracting spatial features and the other ConvNet for extracting temporal features is done. And then at the end, you just flatten it with the dense layer. You have your softmax layer that will output probabilities for each of the classes. So I'm not so sure of the explanation for this part. I mean, if it was clear enough, but if you have any question, you can ask. Okay.
Hello. Okay.
Yeah.
Sebastian, you can continue after the section. There'll be time will be given for questions and answers, so you can continue.
Okay. So now let's look at a notebook implementation of the model I just described. It will actually be a simpler version, so it won't have the spatial temporal front end thing. We just have this part. So the implementation was done in TensorFlow Keras. So here you have the inputs. I just showed the code and I want to run everything because it takes some time to run, but you can look at the code. So I created a function called readGIF that will read the input data. So here I was working with data that I collected yesterday from Google Images. So instead of using videos, to make it easier, I used GIFs because they're smaller and they are easier to read. So here, the problem I worked on was classifying between kicks and punches for martial artists. So one example of data is this. So this GIF shows a kick by, I believe, someone who does karate. So the model should be able to look at this and predict that it's a kick. And the other category is punches. So yeah, for instance, this is a punch. So the model should be able to look at it and tell that it's a punch. As you can see, the data is not a lot, so don't really expect the model to learn anything. But this is just code that shows how the model would take in the data and how the model itself is built. So there's this generator, this generates dataset class that generates the loader for the dataset loader to be passed to the model. So this one, we don't really need to focus so much on it. Then there's the model. So the first most important part of the model is obviously first defining the inputs. So the input shape is going to be like this. We have the number of frames, so frame number, the image width, the image height, and the number of channels. So here I kept it in colors, so all of them were defined here. So the height of each frame is going to be 200, the width is going to be 200, the number of channels is going to be 3, and the number of frames is going to be 50. So each video input is going to have 50 frames of width 200 and height 200. So once that is done, we can start building the extractor. So for the extractor, instead of building your own image convolutional neural network, you can just use one of the pre-trained models like a dense net or something, and then you will extract its output. But here I built my own. It's kind of inspired by the VGG model. So you add a convolutional conv2D layer, an activation function, so the relief function, batch normalization, and then you repeat the process. So this is what you would typically have for a model that classifies images. But then this model is going to be used in a time distributed way. So it happens at this line here, right? So you will have the input data, and then you apply the feature extractor on it. But then before you apply the feature extractor on it, you use the time distributed wrapper around it. So Keras is very convenient for this, even more convenient than PyTorch, because it gives you this time distributed wrapper. So what it will do is, if you have an input with the number of frames coming first, and that has 4 dimensions in total, when you use the time distributed wrapper around a model, it will take the last 3 dimensions and apply your model on it alongside this axis. So here what it means is that for the video, it will take this, which is an individual frame, and apply the model on each of the frames that you have, which will be the number of frames. So here we have 50 frames. So the model defined here will be applied to each of the 50 frames separately, and it gives you a series. Now, usually with the convolutional neural network, for images, you would flatten the output. So you do the same thing again, but it's important to flatten the output of each frame separately. So you've extracted features from each of the individual frame, and you flatten them separately. So you use the type distributed on the flatten on the flatten layer, and then you apply it to the extracted features, so the image frame features. This can be a bit tricky because if you don't wrap the time distributed around the flatten, it will flatten all of them together, meaning that you get just one big vector, and you won't get the temporal information that you want to use. So after that, we can use this. Okay, I called it model M. So model M is just a 1D convolutional neural network. So here we have a 1D convolutional neural network, and here a 2D convolutional neural network. So the 1D convolutional neural network is used for time series. So yeah, it can be used for all sorts of time series. It can be used for text. So usually input that comes in the form of a sequence. And because we just got an input that was a sequence of image features for each frame, we can now apply this model on it. So we apply this model M on it, and then we can now flatten the output of this sequence. And then we just apply this model with the softmax activation function, and we have our output. So when you build the model, this is what you get. So the input, the time distributed convolutional neural network, time distributed flattening. You have the sequential model, you flatten again, and you have your dense model. So created the data set, and yeah, this is it. So this is when I run it. The values here won't make much sense. The accuracy is going to jump around a lot because the data set is very small. It's like 10 videos per category. But I mean, at least it shows how you would use deep learning on image data. So here is the graph. So the training accuracy goes high quite fast, which shows that the model can at least understand the data enough to memorize the training data, but it doesn't do well on the testing data because, well, the data is not enough for it to be able to generalize. Actually, it's overfitting because the testing loss is going higher, but the training loss is decreasing. So one thing too that is quite important when working with this is it's very easy to make a mistake and get a model that doesn't understand the data. So for instance, if you miss the time distributed wrappers here, you can easily get a model if your model is able to understand the data that is given, so it can actually work on videos. The minimum would be for the training accuracy to increase and get to 1. If you miss some of the steps and the model doesn't understand the data, or you show the model the data and you mess up the dimensions, both the training accuracy and the testing accuracy are going to be low, and both the training loss and the testing loss are going to be high. But since the training loss decreases, at least that's the proof that this model understands the data that is being given. So once you have this, you can now work on various data sets. Yeah, and in the end, you can save it. So yeah, that's it for the notebook. I made it available on GitHub, so this is the URL. So yeah, if anyone wants to look at it later and look at the code to use it with various data, you can go and look at it there. In the next few days, I'm going to change a part of the code because it's code that I wrote like 2 years ago. So I mean, at that time, I was now starting with machine learning. So yeah, the code is not really as efficient as it should be. So even with bigger data sets, it usually is quite slow. So in the next few days, I'm going to refactor the generator part, especially to make the code more efficient. Yeah. So this is the URL. Now, let's look at other current areas of work. So here I'm going to talk about things that are done a bit more in terms of research, because deep learning on video data is something that is very new. It's not something that people have been working on for a long time, and that's partly because of the limitations in terms of computation data. And that's one of the reasons why most of the companies that actually do really valuable work on it are companies at places like Tesla or Google. Yes, just something by the way before I continue with this. So one example that I didn't mention where I was talking about the applications of deep learning on video data is self-driving. So Tesla, that is a self-driving company, does a lot of deep learning with video data because video data or video streams are actually what the car is going to see in real time when it's driving itself. So yeah, when looking at current areas of work and current areas of research, one of those are combinations. So when we talk about multimedia, there's multi inside. So it's a lot of different media. So one of the things that could be very helpful is combining different media. So let's say adding sound data to the video data or adding text data. Here, for instance, I was able to work with GIFs because I wasn't looking at sound. I was just looking at classifying punches or kicks based on only the images or based on only what we can see. But sometimes it can be useful to use the sound data too. So for instance, when we look at the speech reading example or the lip reading example, that one can be very useful when you don't have sound, but can also be useful when you have sound and you want to generate, let's say, subtitles. So one of the reasons why you would want to do that is you can generate subtitles based on the sound alone and then use the, the lip reading model to also generate other subtitles and match them to be able to check if they actually are the same, or even combine them to increase the accuracy of your subtitle generation. Another thing that we can add is text data. So for instance, that one, you can do the opposite of what I just mentioned. So for instance, you have a person that is speaking, you don't have the sound, but you have the subtitles that the person could have read. So if someone is talking, you have a video of someone talking, but you don't have the sound, but the video comes with subtitles. You can use the subtitles and the video to now generate the sound that the person would have made when talking. Another thing too is continuous data. So here I've mostly been talking about classification, and the code that I provided was code for classification. But when we talk about deep learning with video, it can be very useful to be able to generate sequences instead of just classifying. So for instance, one of my colleagues that was working on sign language recognition, instead of just classifying, he was able to create a model that generates the sequence of text that corresponds to the video. So even when I'm talking about things like, let's say, generating subtitles, all these things are sequences and not just classes. So you would like to have a model that can generate sequences instead of just classifying. And there are various ways of doing that. Some are more efficient than others, and some are currently being researched on. So one simple way is to use an encoder decoder. So you have an encoder that will encode the video and the decoder that will decode it to text or to any other format. So that can be useful, but it is usually limited to sequences of a specific length or has a maximum length. So the approach my classmate used for the approach he used for the sign language recognition was that he would cut the video in parts. So he will have a model that will be able to identify parts where the person is not signing and separate the video in different inputs, then pass them to the encoder decoder that will generate the sequence of text, and then tie the sequences of text together, which can be very useful because usually deep learning models are not very efficient when it comes to long sequences. So the model can perform well on 5 seconds of sign, but will not perform well on, let's say, a minute of sign. So you take the model that performs on 5 seconds, you cut the video in chunks of 5 seconds, and then you produce the outputs of each of those 5 seconds, and then you put them together. So that will make it possible for you to generate the output of a whole minute or even an hour or several hours of video. So yeah, now that's the end of my presentation. If you want to find me, this is my username on GitHub and Twitter. And if for any reason at all, I don't really know why, but if you want to email me, this is my email. Yeah, any questions?
Thank you very much, Sebastian.
And
Okay, please, if you have any question, kindly unmute yourself and ask your question, please.
Hi, Sebastian, and thank you for your presentation. I have a question. I'm John. Good. So, could you go back to the slide where you talked about the dimensions, 1 by 29 by 128?
And this,
Yes. So, in your presentation, you first mentioned that the video is a 3D. Of course, we have um, the frame, which is like an image. So for instance, 128 by 128, and then it is time distributed. Yeah, but in this form, I'm not able to see that time factor in that thing that you've written. So the 1 by 29 by 128, and so could you come again? Where is the time factor there?
okay. So first, let's identify where exactly the image is. So as you said, the image is this, the 128 by 128, but then the by 1 2 is there for the number of channels. So since it's in black and white, you have 128 by 128 by 1. Now the time dimension here is the 29 because you have 29 frames in the video. So those 128 by 128 by 1 for the image, you have 29 of them,
Good.
meaning that you have 29 frames in the video. And because they come in a specific order, that's where the time aspect comes in.
Okay. And what's the first one also standing for?
Okay, the one here is just the batch size.
The batch size.
So the dimension for the video is just this, but the batch size means the number of videos that you are passing through the model at the same time. So typically when you are training a model, you can have a batch size of 32. So the model will look at 32 videos at once. So here, that means the model takes only one video at once. This one can be arbitrary. So it can be 1, it can be 50. It's just the number of videos you pass at once. It mostly depends on your memory and things like that. But the most important part is the 29 by 128 by 128 by 1. So this part is the video.
Okay.
Okay. Yeah. Thank you, John. This is a very great presentation, and I want to ask, still on this page, this slide, when you were talking about the time distributed wrapper, where you had to feed in some inputs from the flattened layer. Okay, so like, what is the dimension of the flattened output, and like, why did you provide 10 units for? Why did you use 10 as a kernel size for your 1D convolutions?
Okay, so okay, I think to answer this, it will be easier to go back to the code, since I think there's the model summary there.
Okay.
Yeah, so the dimensions that I mentioned there can be seen here. So the none here is the batch size. So this is the most important part.
Okay.
The 128 by 128 is replaced by the 200 here because I'm taking larger images, and there's 3 because here I'm using colored images instead of black and white images. And the 50 here is the number of frames, so the time dimension.
Yeah.
So now this is passed through the convolutional neural network, so the dense net model, and this is what it outputs. Because it was time distributed, it did it on each individual frame, so the 50 is not going to change, but the image was reduced to this 22 by 22 by 64 instead of 200 by 200 by 3. And typically you would want to flatten this. So now you do another time distributed flattening. So since that 1 2 is time distributed, the 50 here is not going to change. but then this is going to be flattened to give you this. So I think we can do the calculation. If we take 22 times 22 times 64, yeah, it will give you 30,976. So when you flatten it in the time distributed way, you get this. So each of the individual outputs of the next debts were flattened and you get this. So you have a series like you have any other type of series. So even for text or anything like this, you have a series like that of length 50 with this.
Okay.
And then you pass it through the sequential model, and this is what you get. And now you do another flattening now, but this one is not time distributed. So the 48 here won't change, and you get 480. And now you can pass it to the dense model, to the dense layer.
Yes. So the part that you spoke about, the conf 1D, then you passed in 10 as your kernel size and a stride of 2. So like I want to find out more about that part.
Okay. Kernel size of 10. Maybe there was a particular reason at the time why I chose that kernel size and that stride of 2, but I can't remember at the moment. It was a long time ago. But one thing I know is usually when I use large kernels, one of the reasons sometimes is to reduce the dimensions. So the larger the kernel size, typically, the smaller the output would be. Yeah, I think so.
Yeah, so, because I'm thinking of the fact that there's a large dimension, like the dimension is very large for you to use a smaller kernel, if that is right. And so I was thinking maybe you using a larger, how do you call it? Maybe a larger kernel would have helped.
Yeah, maybe.
Yeah. But how many classes were you working with?
Okay, so for this specific codes, I was working with 2 classes, so the output size is 2. But when the project I worked on for the lip reading project, it was, I can't remember the number of classes, but it was close to 500 classes because we're classifying the lip movements in terms of words. Yeah. So the number of classes was the size of the vocabulary of what we're working with. So for instance, you will have a word like president, and you have videos of someone saying president, and the lip movements of the person saying that's one unique word. And you will have the same thing for other words, and that would be the number of classes.
Okay, because I was like, in this case, if you are just classifying this the particular input into whether it belongs to class A or class B, this should have required probably using a binary cross-entropy loss instead of using as a sigmoid loss. Final layer. Yes. So instead of using a softmax at the final layer.
Yeah. Typically, I wouldn't work with 2 classes. What you just said is true. Usually with 2 classes, you would use a sigmoid. Yeah, so here instead of the categorical, it would be binary.
Binary, yes.
And here instead of the softmax, it would be a sigmoid activation function. Yeah, but since I wrote this code with like more than like around hundreds of classes in mind, usually that's what you would do. So for people who want to edit this code to work with just 2 classes, you'll have to make the changes that he just mentioned. So here and here.
Okay. All right, thank you.
Is there any other question for Sebastian? Okay. Sebastian, is there anything you want to add before we end the section?
I didn't hear.
Is there anything you would want to add before we end the section? Since I think everyone has a question. If no, we can close.
Nothing in particular. Just that it was nice presenting here.
Yeah. It was such a great presentation. Thank you very much.
Yeah.
Okay. So we've come to
To join our YouTube channel, kindly hit on the subscribe button. Hey aighana, like, subscribe and share.